Now we have the last talk in the session, another Google talk. And Marcus is going to talk to us about language evolution. Very exciting.
Thank you. You're all my hostages before lunch, so I hope you're paying attention. Otherwise, I won't give you lunch tickets. So thanks for coming. You all came particularly to my talk, I hope. And I'm going to talk about how we at Google, we started with a configuration language. We had its challenges, and we've been able to very gradually improve on some of the aspects and doing it in place. Right, so a little bit quick overview about GCL. I'm not going to dive into the language. Other folks in the workshop will go into more details. It's a declarative functional language, and it's used to generate protocol buffers. The schema, the dialects that Alex was talking about, most of the time they're a protocol buffer definition. There are ways to augment that and provide additional information, but most users don't. It was created in 2003, so 20 years this year. Yay, happy birthday. And the first couple of years, because the usage was relatively low, they were able to roll out a number of significant changes to the language itself. Its usage grew very quickly, and very soon it became impossible to change. For folks who are, some folks might have already seen this XKCD, where a user is complaining that the developers broke their workflow because they've stopped the CPU from overheating when the spacebar was held down. So no matter what your language or system does, some people are depending on that for their workflow, often in critical ways. Same for GCL. There were a bunch of things that the maintainers deemed as misfeatures, but users are either depending on that particular behavior or had worked around it. So if you fix the bug, the workaround would stop working and their system would start misbehaving. So if we wanted to change how it behaved, we would have to coordinate with every single user who was depending on any particular behavior. And that very quickly becomes intractable. So there were a bunch of things that people wanted to change to improve in GCL. Many attempts were made. Some were new configuration languages. Others were systems that targeted particular use cases of GCL. They all basically failed. And some of the two I wanted to highlight here are languages. One had better semantics, but with different syntax. They weren't able to figure out how to roll it out. The other one was better semantics, but they kept the same syntax. If we don't change the syntax of the language at all, surely we can make a change to how it behaves, right? Right, everyone? That also didn't work. Basically, it came down to they were better, but not better enough to justify all the cost of migration. To break it down a little bit, how we sort of rationalized what didn't work versus what worked in very small text. If you want to change GCL in this case, or for most systems, most configuration or programming languages, to a different one, you have to rewrite all the code that's necessary to rewrite. If you change the syntax, you have to rewrite a lot. If you don't change the syntax, you have to figure out very specific changes that are even subtler to detect to behave under the new language, under the new changes. This is very expensive to do manually. But sometimes it can be automated. So, but those first few attempts weren't able to solve this problem. Second, you have to rewrite all the tools that work with the code. The systems that take the configuration and do a push to production, or change the user permissions, whatever it is. You have to rewrite all those tools that work with those. So, a lot harder, but often you can find those. There's ideally a countable number of APIs that you provide to your users, and you can find a user rolling out your change can find all those cases and say, oh, this was running the program in version 1, now run it in version 2. A lot harder to do, a lot harder to coordinate, but still, okay. We can still see the top of the mountain that we have to climb. The third one, even more challenging, and if we had a solution for this, we should use it for better applications and changing configuration languages, you have to rewire everybody's brain. If you change from an old system to a new system, everybody has accumulated knowledge about how to interact with that old system. And if in the new system the knowledge doesn't carry over, that's often a cost that most people are not willing to pay. So how do you solve for those when you're trying to make an improvement? Then there's other things that I included about how to make it easier. You have to need a way to verify that a change is correct. Not all the uses of configuration we had that out of the box. For some of the, this is going to be a dexterity check on me. If I can click on that button, yes. Thank you. So not all the systems that we wanted to change had that ability, but we were able to add it. At the time when those two attempts to change to replace GCL were created, those weren't available, so that was a significant barrier to making any improvements. And finally, you need to be able to do it incrementally. If you have open source, if you're open source and have users in different companies, not all of them are going to be migrate at the same time, obviously. Google, we have the mono repo, and we have many teams using the language in different parts of the company, and they work under different constraints, so they don't want to all deploy your new version as soon as the bits are ready from the oven. You need to be able to control the rollout, and in case something happens, you want to provide a mechanism for them to revert back to the old behavior. So these 5 problems were not solved for those earlier attempts. And additionally, so that's why they failed. But we still felt that there were improvements that we could be made to the ecosystems, of the configuration ecosystem, by changing the language, changing the tools available, that made it work for us to keep exploring. So number 1, GCL, some programs in GCL were so large, needed so much memory, so much CPU, you couldn't buy a workstation with a motherboard that accepted enough RAM chips to run the program. And sure, you could plug in a bigger disk, but still, the limit of that, you pass it and you hit a productivity barrier way before that, right? So that was one problem. Another one was complex semantics that people have been kicking the dead horse for a while already in this workshop. We thought we could make them better. And the third, for reasons, the earlier dialects of GCL used many more APIs that were available, resulting in slightly different semantics for several of those dialects. So building tools that worked with each particular dialect was impossible to do, because you'd had to basically mirror all the options and all the combinations of wiring the APIs together if you were to provide, say, a debugger tool, for example. So these were the problems we were aiming to solve within the constraints from the previous slide. And our breakthrough idea, how we did this, was let's just focus on fixing the critical problems and change as little as possible. So how do we, what we arrived at is, let's keep as much of the language as possible, copy all the bugs from the original implementation, reproduce the behavior, but just change the implementation and see what that would enable us to change. The result was we were able to have a much faster implementation. We called it GCL2 because numbers. It turned out to be 10 to 100 times faster, 10 to 100 times more memory efficient, just because we knew what the result was, so we could optimize and implement it in a different way. Some of the complex semantics were improved. We tried to limit that because, again, to the previous slide, change as little as possible. If you try to fix a lot of bugs at the same time, that makes it harder to track what behavior changed because of what fixed. So we tried to limit that. And we picked a few of the APIs that were available and just focused on those and ported folks over to these reduced set of APIs and built facades for a couple others and deprecated a small handful of them to sort of keep the ecosystem simpler. So why did GCL2 worked? We avoided rewriting all the code as much as possible by matching the semantics of the original. We reduced the number of APIs that we had to deal with and made them compatible or wrote facades to work for some of the use cases. We avoided rewiring everybody's brain. Good. Sorry if everybody was looking for a sci-fi solution for some other problem you were having. I don't have that. We did that by the language changes that we made were focused on things that we speculated with high confidence that were not in people's mental models. So edges of the language where people rarely understand, they always have to look up or even don't look up how they work. They just say, I'll just run the program and see what happens and try to guess, to rationalize what the output was. So in those corners of the language where different features interacted, we saw as an opportunity to change the behavior. And that proved correct. We built mechanisms for verifying the result was unchanged, and that made us a way for finding, oh, this program behaves the same or behaves the same with this change, we can switch it over. And we built a mechanism to do it incrementally. We switch over that program. If it behaves correctly, it continues to use the new version. If it doesn't behave incorrectly, we made a mistaken assumption, we can revert back and then debug and analyze what the problem was. So that's why it worked. And based on that approach, we still have other things we want to improve on the language, on the ecosystem. And we're going to do it one small change at a time. From what we call GCL1 to GCL2, there were a number of differences all baked together for reasons. Now that we have a sort of a better platform to make changes on, we're doing it one change at a time, one bug fix at a time. We're focusing on simplifying the semantics of things that users find error prone, things that are easy to make mistakes with, like dynamic scoping, and adding constructs and other replacement that are easier to use. And we've used these techniques to roll out several changes in the last couple of years already. So it's actually worked out. The GCL2, for context, took us about 10 years to roll out completely. And in the past couple of years, we've rolled out like 5 to 10 smaller semantic changes. So the one remaining challenge is when there's an output difference, it's hard to tell what the cause of that difference was. You change the interpreter somewhere in the evaluation, something changed, one branch was taken that was different, and the result is now you have 10 times the RAM. You have to find what the behavior change was that resulted in the different output and track it down. That can be very hard when the programs are very large. Even when the programs are small, it can be very hard. So to flesh out a little bit more how we're doing it, because we have a mono repo, we're using what we call large-scale changes infrastructure. For anybody who hasn't read the software engineering book, I highly recommend that, and there's a particular chapter on large-scale changes that is very relevant to what we're doing. It basically has the high-level strategy about what we're doing and how we do it. We have a tool to validate each effect of a change on the whole, and we can run it on the whole repo. We have a pipeline that basically takes all the source code in the repo and applies the change, and we can use that to identify, oh, this set of programs are not affected at all by the semantic change, correction, don't appear to be affected. The evaluation path might actually change, but the result doesn't change. So if the result doesn't change, we assume that it's safe to move to the new version, and we move it and see what happens, and do that over and over again. We're prioritizing changes that simplify the semantics because analysis is hard with some of the semantics that we currently have, and we have the theory, which seems like it's on track, that if we pull out some of the complexities, the remainder will be easier to analyze. And the output, when there are output diffs, those are still hard to debug. So when we make a change to the language, we try to make a change that when the behavior changes, it produces an error. Because if you produce an error, that's often easier to track where the problem happened and what the possible, you got a value that was unexpected, and now you can say, oh, and the fix for that is out of these set of actions instead of just the output at the end change, which could be arbitrarily caused by any other change. And some language recommendations to sort of stoke the fire based on what we've learned. I don't know how this would map to the language that you folks design, but with GCL, we have a bunch of constructs that are sort of interact with each other in basically arbitrary ways. So you can't really reason about a feature based on how it's formalized. You have to say, oh, when this feature A with this feature B are used together, the result is this thing. With this other feature C, it's this other thing. And basically, you have to test all the combinations. So avoid that. Make your language constructs orthogonal, easier to reason about, formalize the semantics for them. Avoid constructs that do too much. One of the more complicated ones for users is how reference resolution in GCL works. It has this combination of things, including dynamic scoping, that basically tries to keep searching until it finds a value that works. It's kind of based on unification and with backtracking, but users, how it's implemented, find it confusing. Another tip, keep the APIs narrow. Ideally, an API that takes a full program and then returns you pure data. That's basically the basis for the validation tools that we have, and it's also the basis for the diffing tools that we offer that other folks in the workshop will go over. Prefer semantics that are familiar to users. So because most users we found are not doing configuration as their day-to-day job, they rarely tend to develop expertise, and we found they would prefer to use constructs that are familiar to them. If you try to come up with something that's very novel, that may be very cool, but we found that most users will just not try to learn them. They'll copy-paste something until it works. And when it doesn't work, basically they'll often give up and try something else. So if you try to give them something that's very unfamiliar, that'll be tricky. Again, make it copy-paste friendly and write formal semantics for your language. Your future self will thank you a lot. And that's all I have.